In this video, we're going to look at some more example problems dealing with limits algebraically. So first example, we'll look at the limit as x approaches 1 of 2x cubed minus 2 over x minus 1. The first thing we're going to do in each and every problem is we are going to plug in the value that x is approaching in for x into the function. So in this case, we have 2 times 1 cubed minus 2 over 1 minus 1 is going to give us a 0 over 0, which is an indeterminate form. So this means that the problem has just begun. We have some work to do to try to change this algebraically. So when we're looking at this, we can maybe try to factor the top and the bottom as much as possible. Maybe we can take out a 2 from the top. So we have 2 times x cubed minus 1 over x minus 1. And then note that we can factor x cubed minus 1 using the difference of cubes formula. This is going to give us 2 times x minus 1 times x squared plus x plus 1, all over x minus 1. And this is now where we can cancel the common factor of x minus 1 in the top and the bottom. And we're left with 2 times x squared plus x plus 1. And now we have a brand new limit problem, so let's try plugging in the value of 1. We have 2 times 1 squared plus 1, which is 2 times 3, which is 6. Since that's a real number, that is our answer. So the algebraic technique here was to factor and then cancel out the common factor x minus 1. All right, the next problem is actually going to be looking forward to something we're going to do in chapter 2, and that is dealing with the limit definition of the derivative. Before we get to that point, let's just do this limit algebraically. So first thing we're going to do is we're going to plug in 0 in for not x, but for h in this case. So h is approaching 0 here. That's what we plug in for. So we have x plus 0 squared minus x squared over 0. That's the same thing as x squared minus x squared over 0, or 0 over 0. And there is our indeterminate form, which means that we have some more work to do. So in this problem, let's take care of that x plus h squared by kind of expanding that term out. So here we have x plus h squared is x squared plus 2xh plus h squared minus x squared over h. And when we do that, we can simplify algebraically by canceling out those x squareds. And we'll be left with the limit as h approaches 0, 2xh plus h squared over h. And note that now we can cancel out an h out of every single term, which allows us to write this as the limit as h approaches 0, 2x plus h. Now we try plugging in 0, and we have 2x plus 0, which is just 2x, and that is our answer. Note that what we're doing here is we're actually finding the derivative of x squared with the limit definition of the derivative, giving us 2x, but we'll look at this further in chapter 2. All right, next problem, we have a limit at infinity. So limit as x approaches infinity of 2 minus 2x squared over x cubed minus 3x squared plus 3x minus 1. And I want to first talk about the how we can do this just with properties of rational functions. And then we'll talk about how to do this algebraically as well. So what we're looking for here is the horizontal asymptote of this rational function. And we know that this is going to be equal to 0 because the degree on the top is smaller than the degree on the bottom. The degree on the top is 2. The degree on the bottom is 3. And because of that, that means there's a horizontal asymptote at y equals 0, and that's going to be our answer. Now let's look at how to do this algebraically. This is going to be something that we're going to do this kind of technique later on in this course. What we can do is, in both the top and the bottom, let's factor out the largest term. So we'll do the top and the bottom separately here. On the top, we are going to factor out an x squared out of both terms. So if you factor out an x squared out of the last term, that's easy. You're just left with a minus 2. The other one's a little bit trickier. What we're doing is we are dividing by that x squared. So we have 2 over x squared minus 2. If you don't understand where that came from, maybe it helps to multiply the x squared back in and see how you get 2 minus 2x squared back. In the denominator, we're going to do the same thing, except we are going to factor out an x cubed. When you factor out an x cubed from x cubed, you're left with 1. Here we have a 3x squared over x cubed. It's like we're just going to be dividing by x cubed each time. 3x over x cubed minus 1 over x cubed. So the reason we're going to do this is, first of all, note that we can cancel out an x squared in the top and the bottom, and we'll be left with just 1 over x times everything else. So 1 times 2 over x squared minus 2, and x times 1 over 3 over x, so we can cancel out an x squared, plus 3 over x squared minus 1 over x cubed. So we're just canceling out x's at the moment. Then we can use properties of limits to rewrite this as the limit of 1 over x times the limit of 2 over x squared minus 2, 1 minus 3 over x plus 3 over x squared minus 1 over x cubed. What we're going to do is when x goes to infinity, 1 over x is going to go to 0, 2 over x squared is going to go to 0, 3 over x is going to go to 0, 3 over x squared is going to go to 0, and 1 over x cubed is going to go to 0. And we can rewrite this whole thing as 0 times, what we're left here is a negative 2 over 1. And that's just 0 times a finite number, which is 0. So full disclosure, if this problem were presented to you, I would recommend doing it the first way. Use properties of rational functions. Know that the limit at infinity is the same as the horizontal asymptote. However, this sort of algebraic technique of factoring out the biggest term is something that's going to pop up later on, and it is very useful. We'll investigate some problems later on in the course where we have to do this kind of technique more often. All right, next problem. The limit as x approaches negative infinity of 3x squared over x minus 1 plus x cubed over 1 minus x squared. So this is let's first of all plug in the negative infinity and let's see what happens. So we plug in negative infinity, we have 3 times negative infinity squared over negative infinity minus 1 plus negative infinity cubed over 1 minus negative infinity squared. And note, this is all just going to come out to be infinity over infinity, infinity over infinity. And we have all different kinds of crap going on there, and we can't deal with any of that stuff. So instead, let's try to maybe break this up first of all to kind of see what's going on. This 3x squared over x minus 1 is a rational function. The top is bigger than the bottom, which means that this is going to go to either positive or negative infinity. We have to determine which one it's going to be, and we can do that just using signs. We have a negative infinity squared and a negative infinity minus 1. The sign is going to be a positive over a negative, which means that the 3x squared over x minus 1 is going to go to negative infinity. The x cubed over 1 minus x squared is the same thing. The top is bigger than the bottom, so it's going to go to either positive or negative infinity. When we check the signs, we have a negative on the top. Negative 1 cubed is negative. And a 1 minus a positive number, it's going to give us a negative number. That's a positive number, so that means that x cubed over 1 minus x squared is going to go to positive infinity. So the form that we have here is negative infinity plus infinity, and that is an indeterminate form. Same as infinity minus infinity. That's just a lot of work to show that we can't really figure out the answer just by plugging in the value. So let's try to simplify this algebraically, see what we can do. And that's going to be doing common denominators. So let's write this as the limit as x approaches negative infinity of 3x squared times 1 minus x squared over x minus 1, 1 minus x squared. So we're multiplying the first fraction by 1 minus x squared, and the second fraction by x cubed and x minus 1 over 1 minus x squared, x minus 1. Combining everything together, and we have 3x squared minus 3x to the fourth, when you distribute the 3x squared, plus x to the fourth minus x cubed, all over x minus 1, 1 minus x squared. And just at this point, I guess maybe we should simplify first. The top we can rewrite as negative 2x to the fourth minus x cubed plus 3x squared. And the bottom we can write as x minus x cubed minus 1 plus x squared. And here the degree on the top is 4. The degree on the bottom is 3, which means it's going to go to either positive or negative infinity. And we just have to check the signs on what we're dealing with. So we need to determine if the answer is positive or negative infinity. And we can just check the signs on the biggest term. In fact, we can even write this as just the biggest term, negative 2x to the fourth, over the biggest term, negative x cubed. And that's going to be the same as positive 2x. And since we're going to negative infinity, this is the same thing as negative infinity, and there's our answer. So this is a kind of complicated example where we have to do a lot of careful algebra with signs. When you square a negative number, it's positive. When you cube a negative number, it's negative. But the big kind of algebraic technique we're doing here is we are combining these fractions with common denominators, simplifying, and we realize that we just have a rational function. And we're just using properties of rational functions. We find that there is no horizontal asymptote, which means that the answer is positive or negative infinity. We just have to do some work with the signs to determine which one it's going to be. All right, next problem we have, x cubed minus 3x over x squared of 2x plus 3. And note that when we plug in 0 here, we're going to get a 0 minus 0 over 0 times 0 plus 3 in square root. And that's the same thing as 0 over 0. So there's an issue with plugging in that number. But what we can do is we can cancel out an x out of every single term. And we'll be left with the limit as x approaches 0 of x squared minus 3 over square root of 2x plus 3, which gives us an answer of 0 minus 3 over square root of 3, and that's negative 3 root 3. So just as easy as that. So the thing I wanted to draw your attention to is just because you see a square root does not necessarily mean that you should be rationalizing the denominator. To see an example where we should rationalize the denominator, let's look at the limit as x approaches 4 of x minus 4 over square root of x minus 2. When you plug in 4 here, you get 4 minus 4, square root of 4 minus 2, 0 over 0. That's an indeterminate form. We have to do more work. And here the algebraic technique is to multiply the top and the bottom by the conjugate of the bottom, square root of x plus 2. So if we do some simplifying there, we can see the reason why we're going to do this. First of all, bring the limit each step of the way. The top, we get x square root of x plus 2x minus 4 root x minus 8. Kind of a gross thing there. But on the bottom, you get square root of x times square root of x, which is just x, minus 2 root x plus 2 root x minus 4, which leaves us with x minus 4 on the bottom. And here we might think, and if you actually bring everything up else on the top, you would still get 0 over 0. And there's an issue there. But maybe at this point we can see that we actually had an x minus 4 on the top to begin with, and an x minus 4 on the bottom as well. And maybe it would have been better to not simplify the top, or don't expand the top. If we did this, we would get an answer of x minus 4 times square root of x plus 2 over x minus 4. And now we can cancel out the top and the bottom, and we're left with the limit as x approaches 4 of square root of x plus 2, which is square root of 4 plus 2, or 4. And there is our answer. So, two morals of the story. One is that rationalizing by the denominator is another way we can cancel stuff out. But also know that you shouldn't just simplify the very first time that you can. And you've got to try to think about, what are you trying to do? And in this case, we are trying to cancel something out of the top and the bottom. And we can maybe see that that thing is done by not simplifying the top. Very difficult to see it if you do simplify the top, or expand the top, I should say. All right. Last problem has to deal with the squeeze theorem. We have the limit as x approaches infinity of cosine squared over 2x plus 1. Since the limit as x approaches infinity of cosine squared x does not exist, plugging in the value is not really going to work. But we do know that cosine of x is at most 1 and at least negative 1, which means that cosine squared of x is at most 1 and at least 0. And that's what we're going to use as our inequality here. We're going to start with our function, cosine squared x over 2x plus 1. And we know that this is going to be at least, at most 1 over 2x plus 1. And it's going to be at least 0 over 2x plus 1, which is another fancy way of writing 0. Then we're going to take the limit for each of these. The limit as x approaches infinity. And hopefully we get that the left and right-hand side are both the same value. That tells us that the middle is the same value. The left is just 0 because the whole function is equal to 0. And the right is 0 because we have this 1 over infinity, which we know is equal to 0. So that means that our function is trapped in between 0 and 0. So we can say that the limit as x approaches infinity of cosine squared x over 2x plus 1 is equal to 0 by the squeeze theorem.